Hello everybody, my name is Jan Bayer and I'm currently doing my PhD at University Grenoble Alpes under the supervision of Maciej Korczyński and Andrzej Duda. Today I'm going to talk about challenges related to domain name classification, its design and deployment to an operational environment. So there are two types of domain names at the registration time, benign and malicious. Benign domain names are registered for legitimate purposes with no harmful intention. Malicious domain names are registered by attackers to be further used in all sorts of malicious activities, such as phishing, spam, or malware distribution. However, during the activity phase of a domain name lifecycle, a benign domain can be compromised by an attacker by exploiting a vulnerability at the website level, for example a content management system, or at the DNS level due to misconfiguration. It is necessary to distinguish between the two types as the takedown actions should be different for each of them. Malicious domain names are relisted and blocked at the DNS level. However, such an action, if applied to a compromised domain name, would cause collateral damage to legitimate services running on it. It is necessary to only remove the malicious content from the web server and keep benign services running. In this work, we focus on the classification of compromised and malicious domain names. With 350 million existing domains and over 200,000 newly registered domain names per day, it is necessary to develop domain classification systems that are automated to support intermediaries and help desk operators in their anti-abuse practice. To build such systems, researchers choose supervised machine learning, which needs a reliable source for ground truth data for training. There exists numerous related work for classification at the registration time, such as Predator. A little less attention is given to systems distinguishing between malicious registrations and compromised domain names. We identified several common limitations related to domain name classification. First, some features proposed in previous work are based on privileged data with a restricted access. Second, ground truth datasets are often gathered using third-party services without necessarily having insight into used methods. Some researchers choose to create their ground truth dataset by manually labeling domains, which creates highly quality data but is time-consuming and prone to errors. Also, some samples can be difficult to label and even by domain name experts. I will now present the proposed solutions to these limitations. We only use publicly available data sources so that intermediaries involved in hosting, domain registration, and abuse handling, like law enforcement agencies, could make use of our system. We use 17 features from 10 categories. Lexical features extracted from the domain name, registration data from WHOIS and RDAP, content length, index page related features, homepage redirections, used web technologies, DNS features, Alexa ring, number of hyperlinks, and snapshots from Wabeke machine. As Alexa is no longer available, we propose that it be replaced by the Tranco list in future work. We propose a new method to automatically generate ground truth data for malicious versus compromised domain name classification. We base the method on the differences of mitigation actions for each class. Malicious domains are blocked or removed at the DNS level and thus become inaccessible for victims. The mitigation action for compromised domains usually consists of removing malicious content from the server. It is important to note that there are cases where investigators first remove malicious content to limit the harm as early as possible. If they find that the domain was maliciously registered, they later proceed to takedown action at the DNS level. We design the algorithm for generation of ground truth datasets in a way that we give investigators enough time to take an appropriate action. To generate ground truth data for maliciously registered domains, we collect URLs from phishing blacklists. We exclude URL shorteners, dynamic DNS providers, and free and paid subdomain providers. We extract domain names and collect their creation date and expiration date from WHOIS or RDAP. After 6 months, we again collect the creation and expiration date. We also collect the status codes defined by the extensible provisioning protocol, and we search for domains that are on hold, meaning their status code is either client hold or server hold. In order to guarantee that the data auction is related to the original registrant, we verify that the creation date did not change during the 6 months. Domains that are not expired, meaning that their date of expiration is after the measurement date, but are on hold, are automatically labeled as malicious. For compromised domains, we also collect URLs from blacklists. We verify that the HTTP status code is 200 to ensure the malicious content of the reported URL is present on the web server at the time of blacklisting. We then collect the title of the index page hosted at the Apex domain name. For example, for the shown URL, we will collect the title of the website hosted at example.com. After 6 months, we visit the reported URL and only keep those that return the 404 HTTP status code, indicating the malicious content was removed but the domain remained active. We again collect the title of the website hosted at the Apex domain. Domains whose title did not change during 6 months are then labeled as compromised. Using the automated methods, we identified 3,632 compromised and 12,179 maliciously registered domains. The limitation of our proposed method is that the abuse must be mitigated. If a malicious domain name was not taken down, our automated approach cannot label it as maliciously registered. Similar situation occurs when malicious content is not removed from the web server in the case of compromised domains. This is why we merged two ground truth datasets. One, GT1, generated automatically, and second, GT2 in the picture, consisting of manually labeled domains which does not suffer from such limitations. We investigated the extent of missing values in our unlabeled dataset. We found that only 36.5% of records have a complete feature vector. It is common that data collection suffers from missing values, which can be caused by persistent errors, such as unavailable whois or RDAP information for certain TLDs, or timeout related to HTTP measurements. Given that traditional imputation methods might generate biased results, we propose a system based on COMAR, using multiple models trained on different combinations of removed and present features. This way, we generated 511 models. We also provide a detailed analysis of performance metrics for each model, which enables users to define a threshold based on the intended usage. This graph represents the cumulative distribution function of metrics for individual models. The y-axis represents the fraction of labeled domain names. The x-axis represents values for false negative rate, false positive rate, and Matthew correlation coefficient. Using this graph, potential users can choose the metric threshold based on the needed dataset coverage. For example, if we choose models with MCC higher or equal than 0.8, the system can enable 76.3% of domains of the unlabeled dataset, which is 39.8% more than using only one model trained on records with no missing values. Our unlabeled dataset consists of URLs collected from APWG, FishTank, and OpenFish between January 2021 and September 2022. After removing URL shorteners, dynamic DNS providers, and subdomain providers, we obtained almost 219,000 unique blacklisted domains. We then apply the proposed classifier to the unlabeled dataset. As in the previous example, we choose the MCC threshold to 0.8, corresponding to 76% of classified samples. In this graph, you can see the ratio between malicious and compromised domains in different types of TLDs. While roughly 70% of CCTLDs and legacy GTLDs reported to blacklists were malicious, this value is significantly higher for domains registered in new GTLDs, almost 96%. We also analyzed the age of a domain at the time of blacklisting. We can see that 11% of malicious domains were blacklisted at the same day they were registered. A total of 93% of malicious domains were blacklisted at the most 1 year after its registration. On the other hand, 66% of compromised domains were older than 4 years at the time of blacklisting. Here follows the distribution of popular keywords appearing in a domain name of phishing URLs. Words like online, secure, bank, support, info, or login appear frequently in maliciously registered domains. It is not surprising that such words do not appear in domains that were registered with a benign intent and were later hacked and compromised. This figure shows the importance of this feature to help the classification correctly distinguish the two classes. In this work, we come up with the following contributions. First, we propose an automated generation of ground truth data for classifiers of malicious and compromised domains. This method is fast, highly reliable, and does not require privileged data. Given that it is fully automated, it can be used on a regular basis to create ground truth datasets continuously. We plan on using this method further for reinforcement learning. The whole classification systems relies only on publicly available data, which makes it usable and deployable for intermediaries involved in abuse handling. We introduce a classification system based on multiple models, which allows us to label significantly more domains while keeping a good overall performance. This system was deployed at 2 European TLD registries. We find that 96% of new GTLDs reported to blacklist were malicious and only 4% of them were compromised. Finally, let me thank all who contributed to this project. We thank Benoit Ampo, Mark van der Waal and anonymous reviewers for bringing valuable comments. We thank APWG, OpenFish and FishTank for providing access to their blacklists. This project was carried out within the framework of the COMAR project funded by SIDN and AFNIC, registry operators of .nl and .fr TLDs. Thank you very much for your attention, and if you have any questions, I'll be more than happy to answer them.